All right. Well, welcome to our last last class. We'll talk about contaminant transport. And so I thought I would kind of do a recap of some of the things that we've talked about. I guess we have previous stuff I could use instead of redrawing it. And I guess I'm curious. Not that one. Perhaps this one. Yeah, perhaps that. If I copy this, see if it works. I think it probably will. Stuff. All right. So that's probably an easier place to start than drawing it out by hand. So we've talked about the mechanisms by which fluids get advected down gradient and spread out. We've rationalized it in terms of an equation that looks like this, where accumulation is equal to the advective transport that physically moves the front downstream, and also the dispersive transport, which spreads the front out as it moves downstream, both longitudinally to give us this cantered over part, and also in the case where it's 2 or 3 dimensional, transversely to spread out the plume. We know that in this 2-dimensional case, since the box that's containing our contours is getting larger as we go downstream, the same mass of fluid that's in this larger box will by definition be a lower concentration as it steps downstream. The transverse dispersion causes this bell curve effect if you look at a cross-section perpendicular to flow. If you look at a cross-section along flow, then it might look like this if you keep the concentration at the source constant, or it might look like a bell curve as it goes downstream if you don't. And last time we looked at the expressions that would describe this behavior if, for instance, it was a one-dimensional problem down a tube, in which case this concentration gradient would be 0, and we'd be left only with these 3 terms. And I guess we found out that there are a couple of terms that define our behavior. One is called the Peclet number, which is an advective flux over diffusive flux, or dispersive. And in terms of our problem, advection is velocity times length, and this is advective velocity, and dispersion or diffusion would be our d sub L. Longitudinal. And the other term was a Courant number. We called it, Vetter calls it T sub R, because it's a function of time, and it's a time times length over velocity, times length. Well, I should look to see what it is. No, I should get it right. Or someone can remind me what it is. Sorry?
It's T times V over
L. T times V over L. Okay. T times V over, I'll call it L to be consistent. So, so if you think about, so this describes how advection dominated, actually no, it just describes a pore volume. So it, as you fill up the core, it goes from 0 to 1. As it reaches the end of the core at length L, it's exactly equal to 1. This is, in both cases, these are the advective velocities, and so we could replace these terms with those. We need to use a dispersive component. We define that according to this, which includes kind of mechanical dispersion and molecular diffusion in these two parts. If our advective velocity is very small, then this term disappears and we only have diffusion. And if our advection is large, then this term doesn't change in size and it becomes inconsequential. This is the, I think we didn't call it this, we just call it dW, and the product of these two terms we said is equal to d star, the effective diffusion coefficient that includes this. These are in the limits when velocity goes to 0 and when velocity is large. And so they define our behavior. And so the second thing that we use then to describe this, so if you look at this behavior of this graph between upstream and downstream, so the input curves and the residence time distribution curves. If we look at these behaviors, we get some response which is distance, a relative concentration is just normalized. So I guess the other term that we use, which also is between 0 and 1, as is TR, is greater than 0. I guess it's not limited to that because you can keep on flushing the core after you've completely filled it. So it's not limited to 1. And we can draw the residence time distribution as it comes out, which you've already had some skill in doing. C over C0. These would be 1s. This would be the input concentration going into it. And these different behaviors would be the input. This would be time. This is time. What it looked like here was if it was plug flow, it would look like this. I think we did it the other way around before. And if it was plug flow, it would look like this coming out. We know from velocity is equal to length over time that length is equal to Vt. And of course, as Garrett said, so this is a length, velocity times time. It's the length the plume goes in a given time, and it's often used in as a choice to make a time step for numerical models. So if you divide a numerical model up into a whole bunch of little grids, you don't want the contaminant coming in from the upstream side and disappearing out of the downstream side in a single time step because it has no way to account for that information. And so you can define a stability in running numerical models in terms of a Courant number. You keep it less than 1 in this particular case, where L is the width of the element. So we'll talk about that later, but not today. So, and of course, if this is the case, then time is equal to length over velocity. So this is T is equal to length over advective velocity, kind of. We know that there's some limitations. We know that this length here can equal product of advective velocity times time. And we know that the green is for dispersion going to 0. And what do we have? And the blue would be for longitudinal dispersion greater than 0. I know I'm mixing up my colors, and so it would be like this. And we even saw in some cases that these curves would actually look like this. And so these are the same. This is for plug flow. You get a sudden breakthrough. and all of a sudden it turns on and turns off. We talked about the reasons for this being that it finds some fast pathways down it which allows it to arrive early, which is what this is saying. And we have some constraints on this equation. So let's see if we can get back equatio. So equatio, this expression up here is the expression in Fedder. I guess I could bring it back. If we go up here. So we can think of an aquifer as a core, length downstream. We can position ourselves at length L along the core, and we can write an expression that defines how concentration changes with time at that compliance point, and we find it's defined in terms of the three terms we looked at: relative concentration and pore volumes, or Courant number. And if we program this, which is exactly what I have in equatio, then we end up with a behavior that looks like this. So that's why don't I make it? I want to make it bigger. I don't know why it won't. Why won't it get? Is there a plus? So on the left-hand side, so this is the Rosenstein distribution. So this is the equation. This P is the Peclet number. X must be the Courant number if it's big enough for you to see. I don't think you necessarily need to see the equation, but it's just quoted. So the x-axis here is T sub r. And so the important number that we're interested in is one pore volume, which is the number 1. And of course, if the Peclet number is 55.7 or 100, I guess, the Peclet number, we notice that two interesting ordinates. One is that the breakthrough time at 50% concentration occurs exactly at one pore volume. And that's useful to us because we can anchor it. But it also arrives at finite concentration before one pore volume arrives. So it must be traveling ahead of the plug flow front. And if some of it's traveling ahead of the front, then some is lost behind the front as well. And so this is skirted over. I don't know if I can change this. I think it doesn't like 1,000 as a Peclet number. Don't know why. Is it just the range on this? If this is 1, will it do 1,000? No, it doesn't. For some reason, it doesn't like do 1,000. Don't know why. And so if we change the magnitude of the Peclet number, and it will allow us to run it. So if we reduce it, I guess what you see is that progressively cants over. If we get down to 10, well, when we're still at 38, we're still through this 50% mark at 1, so that's not changed. As we go down to 10, then we've moved a bit right of there, right? Instead of being at one pore volume, we've moved ahead of it. And as we move down to whatever we can get to, can we get to 1, then all of a sudden it's not a very good representation at all. And so for Peclet numbers less than 10, maybe we don't want to use that very simple expression, and you have to resort to something like this. Of course, as you go smaller than 1, if you went to 0.1, then it gets even stranger. It's moved further away from this mark, and it kind of implies that the breakthrough is occurring really early, but it's for a small Peclet number, and a small Peclet number is for diffusion only. There's no advection in the system. So what it's actually saying is that because this pore volume number is so small, it means you're not flushing any pore volumes at all. It's just that the components are traveling independently from one end to the other without the aid of advection. They're traveling by molecular diffusion. So it looks like it's traveling much faster, and it is traveling much faster in this dimensionless time we've chosen, but in real time it would be traveling much more slowly because velocity is 0. So that's it. So that's equatio for you. So that kind of allows us to catch up. So these equations that we've dealt with are useful for being able to show that behavior, and that allows us to say something about this. And so I suppose if we want to understand something about this, we've got enough now to know what the expressions are that control that, or what the behaviors are. It's dispersion is a big part, and we can use pore volumes and Peclet numbers to describe that. But I guess we don't necessarily know exactly what these numbers are. And so we might be interested in getting those numbers to be able to say, can we use this simplified time of arrival? I suppose we should make the case that this is only for Peclet numbers perhaps greater than 10 as a rule of thumb. And I guess the other question we could ask is whether this concentration at the downstream side arrives at the same height or whether it's lower, whether it's reduced. We certainly know that if we looked at this one case where we had dispersion, so if we have a step input, which is like a Dirac delta function, so this is our concentration versus time. This is the input. This is C over C0. Then we know that that would look like this as we went downstream. I suppose if it's plug flow and it's only one-dimensional, you'd expect it to look like this at each of the 3 successive times you might choose. But if it's dispersing, then I suppose you might expect it to look like this, and then like this. So the characteristics are that this, the width of the plume, which we called 3 standard deviations as a length, would be broader. And of course, if the volume that is encompassing the plume is larger, and you still have the same amount of mass that's been put in, then the concentration must be lower. So the peak must go down. So how do we describe those behaviors in terms of the properties that we'd want to get? And so the properties we want to determine are these 2 things. Alpha L, and I guess alpha transverse as well, and also the value of either this molecular diffusion coefficient of TCE in water, or its corrected derivative for the fact that it's flowing through pores. And so how do we do that? So that's what we'll talk about today, and perhaps quite quickly. This says the same as we've talked about. They're figures that are taken out of FEDER. It's a profile that's a cross-section through a hazardous waste site, a landfill, which has a source in it, and it looks at how the plume develops as it goes downstream. And it makes the point that if you have a 2D system where the hazardous waste site is infinitely long, and so you can cut a 2D swath through that, and that 2D swath would look like this in X and Y, but it means that every portion of contaminant that's being carried downstream is restricted to staying in its lane. If you have a finite rectangular area that sits on top of a 3-dimensional surface, and as it goes downstream, it's able to disperse laterally instead of just being confined to its own lane, then you would imagine that since the box is getting bigger laterally, then the concentration profile would be different. And so for a 2D constrained system, it will travel further because it's constrained laterally. A 3D system will disperse laterally, and so that lateral mass will be lost to the stuff that's going longitudinally, transversely. It's going transversely, I guess, for T in alpha T. It's going transversely, and therefore mass is lost. And so if you look like it in cross-section, it'll look like this. This is looking at it in vertical section as it can spread out. And so that's a straightforward message, I guess. But anyway, to be able to figure out exactly what this plume would look like in some time later after it's spilled, you have to know what these coefficients are. These are the same figures showing exactly the same thing. If you change the value of transverse dispersion from a big number to a small number to a smaller number to an even smaller number, if you're not allowing it to disperse transversely, then even if it's a 3-dimensional problem, the concentrations that are trapped within the section that is just cuts through the landfill and goes down the flow gradient will be more and more concentrated. and you can rationalize it. It's the same rationalization as we're applying here. Physically, by changing the coefficient of the transverse dispersion, limiting it so it doesn't transversely disperse, in other words, so it looks like the green curve instead of the red curve, then you increase the concentration of the stuff that's trapped within the section. So, a straightforward point. So the bottom line is, how do we get this value of lateral dispersivity, which is equal to alpha L times velocity plus what we've called d star. So one thing you could do, I suppose, well, not I suppose, we'll look at three things. The first two, actually, laboratory tests, in situ forced gradient experiments, so the three things, and in situ natural gradient experiments. The first one is our laboratory test. So you take a sample back to the lab, you put it in the lab, you put an upstream concentration on it, you wait for that concentration to go downstream, either with or without a velocity, and you measure the arrivals at the downstream location. If you can measure this green curve, whether it looks like the red curve or the green curve, then you can merely fit it to this for a given Peclet number. So you know that the shape of this curve is unique as response to that Peclet number. And so presumably, if you fit the curve to that and you know what the velocity is that you're supplying, you have enough information. If you know the velocity you're supplying, you know the length at which you're measuring it, you know the Peclet number for fitting with this curve, because you know this. The only unknown is d sub L. And so you merely do some curve fitting to be able to do this. So you get the curve at the outstream end of the sample. You fit it so you know exactly the Peclet number. If you know the Peclet number is equal to advective velocity, the length of the core, and dispersion. And so you know this from the curve fit. You apply this, or you could get it from T sub R, I guess. And you know how long your core is, and so you can rearrange it to get dl. If you know dl is equal to this, then you know that you can get this d star. You could run it with a velocity of 0, and the magnitude of dl you get out of it is this. So you know dispersion exactly. You can run it with a higher value of velocity in it, and you'd end up not caring about what this is, because it'd be dominated by this term, and therefore you know what the advective velocity is, so you can figure out what this is. So those are the two cases. So v equals 0, you can get d star, and v not equal to 0, you can get dl, and from dl, since you know advective velocity, you get alpha L. So that sounds great in theory. It turns out to be no good whatsoever. And the reason is that it's certainly good for getting this. So if you do one when there's no velocities in the system, then it will measure the effective diffusion coefficient in your system quite well. But what you'd find is that because this dispersion is a function of two components, right? We talked about this being something that looked like diffusion, but also mechanical dispersion. Since that mechanical dispersion may change, or it seems to change as a function of velocity, then kind of you're exercising that by using a different velocity. But it turns out that this mechanical dispersion is also a function of scale. And so if you think about it, using this diagram here, if you think the spreading of the front, we used this already to talk about the idea that if you take a sample here, it's only water. A sample here might be contaminant. Sample here is water. Sample here is contaminant, etc. And so we use this to explain that's exactly why you get the profile of the concentration along here that might look like this, right? The reason for this, I guess it would be a bit more extreme than that. The tailing is starting way back here and occurring all through this zone here. The reason for this tailing, for mechanical dispersion, is because of this. If you think about only having a small sample, your chance of getting some really big features in there that might be very effective fractures for spreading it is not very large. If you take a sample that only includes this material here, then it won't be very representative of the bigger system. So it turns out that using cores in the laboratory is great for getting values of molecular diffusion in the system because it samples things at small scale, but it doesn't sample things at field scale, which are actually what control this term here. And so you don't get a good representation of that. And so no one ever does this for measuring the mechanical dispersion in these systems, although you can do it. But it's straightforward the way you do it. It's just driven by the things that we've talked about. So that's one thing that you wouldn't do to get alpha L, but you would do it maybe to get what we've called D star, the diffusion coefficient in situ. The other things that you could do would be to try and get around that problem by taking a bigger sample. And so going into the field and doing a forced gradient tracer test. These also suck, as it turns out, and they don't do a very good job for you. And the reason is because they sample a larger volume, but they tend to be run at higher pressure gradients and therefore higher velocities. So the gradient here refers to a pressure gradient or head gradient, but really it's referring to the fact that the advective velocity is much greater than natural when it's just sitting there in situ doing its own thing. And so the fact that you take a well bore and you pump tracer in, and so if you looked at the injection profile, this would be your injection profile into the borehole, right? At time zero, you turn it on, and you inject at some concentration. You'd inject for some time, and then you'd stop, and then you'd actually reverse it by sucking the fluid back out. So I'm not sure how you, I guess you can't really show that in terms of concentration, but I guess if you drew this in terms of a volumetric flow, injection flow, if this was Q versus time, then I suppose it would look like this, and this, and then this, sucking it back out. And maybe, perhaps I'll do this, get rid of this. So what would it look like? Haven't really thought it through, but what would it look like if we looked at concentrations on the downstream side? So I'm just borrowing this figure. So this is the radial injection into a wellbore. It goes in at some concentration, and we stop, and then we pump it back out, and I guess it comes back at some concentration. So I suppose what it would look like on this is that how should I draw it? I'm going to draw it. This is the output I'm going to draw on this side. And of course, we're measuring it at the well bore. So C over C 0 versus time at the output would look like what? I guess as you inject it and you measure it in the well bore, the concentration would always be your injection concentration, which would be 1. But then what would it do? So you'd start sucking it back out. So I suppose initially it would start off at this, but you could imagine that a long way away from the well bore, I'll come back to this, but I just want to do this. So you could imagine that the amount of fluid that you've injected has reached this front, which is this radius F, front radius away, but it might not be a sharp front. It might have spread ahead of the front, and it might be empty of contaminant behind the front. So that when you pump it back, you'll pump in the pure concentration that's near the well bore for a while, but then you'll also get the effects of this front as it gets closer to the well. So I suppose it would look something like, be happy to be concentration of 1 for a while, and then it would drop down as it would get down here. And I suppose this, this one here, where you've recovered all the water out, if it's a sharp front, I suppose the front should have looked like this. Another color. Let's go crazy. I guess red might work. So if it was a super sharp front and no dispersion ahead of it, I guess it would look like this, right? And the more that this return front is canted over, the more dispersion you have in it, and therefore you should be able to fit a solution for this injection scenario to look at that. We won't talk about that solution because people don't use these, because what you induce in it is some artificial dispersion. And so I'll go to the figure to kind of suggest what that is. And that is, if you think about injecting fluid at your well here, you know from flow nets that your flow system from that, see, we come back to all this stuff at some stage. Well, I could even draw it using this. Man, this is going to be fantastic. Can you believe how good this is going to be? These aren't the best flow nets because I've already violated some of the tenets, right? So it doesn't matter. So you remember flow nets? You remember that you can get the volumetric flow rate, which is equal to the number of flow tubes divided by the number of drops multiplied by hydraulic conductivity times the head drop across the system. So long as you draw the flow net that satisfies the fact that all these intersections are at 90 degrees to each other between the streamlines, which are red, and the circular equipotentials, which unfortunately are also red. So long as these intersections are at 90 degrees, and so long as these cells are roughly equidimensional, 1 by 1 in terms of this length and this length, not quite, but close enough. So this one would give you the volumetric flow rate is equal to number of flow channels, 1, 2, there are 8. Number of drops between the well would be 1, 2, 3. Whatever the hydraulic conductivity is, and whatever the head drop is between the outside and the inside, gives you your flow rate into the well. 2 seconds, incredibly powerful. My reason for mentioning this is that you know that within each of these flow channels, these flow tubes, Q is constant by definition. And so the fact that close to the well bore, the cross-section area is small, so the velocity must be high. Long way away from the well bore, the cross-section area of flow is big, and so the velocity must be small. So this velocity would be small, so this velocity is big. And the problem is that you get geometric dispersion happening as a result of this because of the variable flow rate along the length of the tube. Actually, it's not such a great illustration. The next one is a much better illustration. And so in reality, no one ever uses these methods to try and get a magnitude of the dispersion in. But you can imagine that if you have a solution to this, and there is a solution to the concentration that you get if you inject at some concentration for a given time, and then you withdraw for a certain length of time and look at the concentration profile that we just drew further up in this form, this black line here, or the red line, you can curve fit to these profiles, and you can pull out a value of dispersion coefficient, dl. And if you have dl and you know what your velocities are, you can get what we've called the coefficient of longitudinal dispersion, alpha t. So this has units of length squared over time. And since it's equal to alpha L times velocity, this has units of length. So we can get that out of it. But no one ever does that. That's why I'm not dwelling too much on the details of it. You could also do a twin well tracer test, and no one does that either. And that's even much easier to illustrate why you wouldn't use it. So again, you think of a flow net that describes this. This is the injection well. This is the recovery well. The blue lines are the streamlines. The red lines are the equipotentials. This mid-equipotential is half the head drop between the upstream and downstream. This equipotential here goes to minus infinity, then comes back from infinity into the other side of the flow net, which is right here. That's kind of what it is. And so if you think about these flow lines, then I suppose you could think about the head drop between upstream and downstream. So this is delta H over 2 and delta H over 2. So these are the heads that you have in these wells. I suppose the head gradient along that portion, it's not linear, but it's not too far off it. It would be some close to that. It would actually be much steeper closer to the well. A bit like that. Not so flat here, because if it's flat, then it means it has zero velocity. But you get the picture. If you want, you can think of it just as a straight line, but it's not. Because you know it's not a straight line because the area which it's flowing through changes along its length, and you know each stream tube has a constant flow rate through. And so the point is that this would be the flow line as you go between this point and this point. The streamline between this one is much longer, has to be the same gradient, and so by definition, has to be the same drop. The drop between upstream and downstream is the same. It flows much longer, so the gradient has to be smaller, and so the velocity has to be smaller as well. And so that means if the velocity describes how long it takes, time is equal to length over velocity, I think. Length over time, yeah. Then the time it takes, if the velocity is smaller, is much longer, even if the length was the same. The length it's traveling is actually longer, so the length is longer and the velocity is lower, and so the time it takes to get there is increased. And so if you think of these flow channels as each carrying a packet of contaminant, and each being one of these flow tubes with a breakthrough, the one that travels fastest, has the fastest velocity, will arrive earliest. The one that travels next fastest, next to it, will arrive later and later and later as you go down the stream tubes. And so you'd expect that even if you had zero mechanical dispersion in your system, your breakthrough curve well, let's think about it. What would the breakthrough curve look like? We can draw it. This is time. This is C over C0. I suppose we could think about stream tube number 1. Maybe that breaks through at this particular time, which is equal to, bless you, time is equal to length over velocity. This would be the breakthrough for stream tube number 1. It carries its packet down, it arrives here, the front, with no dispersion about the front, arrives, and everything that arrives after it has this amount of mass in it. But of course it's diluted by the fact that the mass, no mass is coming through these other stream tubes. The next stream tube that breaks through is going to be later. It's going to have a certain amount of concentration in it. And so they'll start looking like this. You can imagine. And so the point being is that there's some breakthrough curve that looks like this. It certainly isn't a breakthrough curve that looks like this. And so it has a breakthrough curve that looks like it's got dispersion going on, but that's not due to the fact that water is flowing along different path lengths. Our kind of definition of mechanical dispersion is that they arrive downstream at different times and look like a bell curve, not a very good bell curve. Look like this bell curve, both longitudinally and transversely, because of this mechanical mixing effect. That's not happening at all. We're assuming that these all individually arrive as plug fronts, but it looks like there's mixing going on merely because, I guess we'd call it geometric dispersion, or that's what I'll call it. And so the mere fact that it's flowing down different stream tubes, and of course the stream tube that goes out here to minus infinity and then comes back from plus infinity is going to be infinitely long into the future. And so the mere fact that you see dispersion in it, but it relates in no way to the mechanical dispersion of your aquifer, it's merely set up by this particular flow geometry that's there. And so if it's a function of this flow geometry, it's not telling you anything about this process, which is what you want to know. And so again, for the second one of our in situ methods, it's rarely used. So in the lab, for low flow velocities, you can get dispersions. In the field, if you use either push-me-pull, huff and puff tests, they're sometimes called, you inject and you recover, huff and puff, I guess, or injection recovery tests or single well tracer tests don't give you a very good result because of this geometric dispersion and for the fact there are the large velocity gradients. And also twin well tracer tests don't give you a good result, again, for geometric dispersion. And also because the flow velocities are much larger than in reality, in situ. So the second of our in situ experiments would be a natural gradient experiment. And as the name suggests, the gradient is the natural one which is in situ, which is undisturbed. You're not applying a pumping gradient on top of it, but you're merely using the natural gradient that's occurred. And so the idea is, and this is an experiment from Canadian Forces Borden, an experimental site that the University of Waterloo in Ontario used to use. And it's a sandy aquifer. Underneath the aquifer there's a confining layer of clays, so whatever you put into the sandy aquifer can't disappear downwards. And they introduce at some point an experiment where you have a mixture of some components. These components are just chloride salts, but also in the cocktail there was some TCE and PCE introduced at the same time and all together. This is just plotting the results for the chloride ion that is carried downstream. And so at day one, you dig a hole, you put this stuff in the ground, You fill the hole back up again. It's only a meter or a couple of meters down, and so if you take thin capillary tubes and push it into the ground and then suck the fluid out of it, you can take samples. And so you can do this all over the place like a pin cushion and get a concentration profile, which is exactly what these kind of profile is. This garbled profile are in some units. Let's not worry about the units. You roughly know where you measure heads both upstream and downstream, and also crosswise, and so you know your gradients of heads either upstream or downstream. If there's no gradient laterally, you take this as being the direction you'd next look in. Maybe if you know the heads and you also know the permeability, then you know that the velocity traveled is equal to the hydraulic conductivity times the head divided by porosity. And so if you know this, you know that length is equal to time over velocity. Is that right? Length over time? Yes. No. Length. Time. Times, yes, I heard you. Didn't register though. So this isn't lambda. So length traveled is velocity times time, of course. So this would give you length is equal to velocity times time. So you'd go here. You start putting your tubes in the ground. You take your profile after 3 months, and then again after a year and a third, and then after a year and a half. And you'd get these profiles. You'd realize that these profiles, if you looked at them along this here, would look like, can't draw it on side very well, these would look like your bell curves of varying width and height. This magnitude here would be what we've called before 3 standard deviations, because it looks like a bell curve. And you'd use that information to be able to define the behavior. Sorry, if you recall, I'll come back to this, but I'll just go back to the last thing that we talked about when we're describing this. We talked about this term here. The equations of our bell curve for Gaussian distribution are that 3 standard deviations, which is, this is wrong, right? It's just this length here. Is 3 times the square root of 2 times the this is dl if it's in the longitudinal direction, and dt if it's transverse, and this is the time since you started your experiment. So we're just going to use that. And so this figure is set up in that particular way. Hopefully to do that. So these are the steps. So you measure your plumes, you figure out how far down gradient you've gone after 85 days and 38 days and 61 days, because you know the distance between where you started and where the center of mass of that plume is. So 9.5 meters, 38 meters, etc. If you know how far it's traveled in a given time, by definition, you know the actual velocity of the plume. Of course, you might want to have got that from doing a pump test beforehand to know what the permeability is. If you know what the permeability and porosity is, you could estimate this, but you can also calculate this from the center of mass of the plume. This, right? 85 days, you know, 9.5 meters downwind, and so there you have an adequate velocity. You know that you can evaluate your dispersivity from this, because now you also have this length, This length here is 3 sigma after 85 days. I can't see exactly. This looks like this length here is 3 sigma at 462 days, which is what this is. So this must be, yeah, looks about right. This is 5 meters estimated. This is 14 meters. And I've just scaled it off from here. These are the times at which it occurred. Times are in days. So if you want your dispersivity in days, you can just use those directly. And you get these. They turn out to be an average value if you just add them all together and divide by 3. Obviously, these these distances haven't changed very much, but the timing has. So those would be changed dispersivities. And you can also then, if I change to red, you can also do the transverse dispersivities. And so the transverse dispersivity, I guess, would be, this would be 3 sigma. 3 sigma at 465 days. This would be transverse, and this would be longitudinal. So very straightforward. And the average values of the longitudinal one are 0.019 meters squared per day. The average values of the transverse are roughly a third of that, which is actually very convenient, as it turns out. So dt is roughly a third d sub L, as it turns out, just from these two numbers. No particular rhyme nor reason to that, but it'll turn out that that's perhaps not a bad rule of thumb. And of course, if we wanted to convert this to values of our alpha L, so we've measured dl, and it's equal to alpha L velocity advective plus d star. I suppose if it's a sandy aquifer, we can assume that V is large. Therefore, d star goes to 0. If d star goes to 0, and we know what the advective velocity is, then alpha L is equal to the measured value for the dispersion that we get divided by the advective velocity. Nothing more than that. Right, just manipulating it. So it's really kind of a two-step equation. Know what the solution is in terms of the bell curve, the Gaussian distribution. 3 standard deviations is just the length of the plume from its center of mass, either longitudinally as it travels downwind or transverse as it travels downwind. And we can use those values to represent the magnitudes. We can solve for the value of what we call either d sub L, or d sub t. If we know what d sub L or d sub t are, we can get the values of the coefficient that is independent of the velocity, right? If we want a coefficient that represents the aquifer, it would be alpha L, because we've thrown away the velocity. It's only representative of that particular velocity, and so we'd like a term that describes our aquifer. And I suppose the other thing we could do is we can also get d transverse in the same way. And you know that, but the point of mentioning this is that this advective velocity is the velocity down gradient. The advective velocity in the transverse direction is 0 by definition. And so, of course, if you use 0 here, you get nothing here. And so it doesn't work out. So the advective velocity is the maximum value, which is in the direction of the longitudinal dispersion. And you see, I guess you could tell from these results, since the profiles of these contour plots, concentration fields, are extended in the down gradient direction, you know that the dispersion in that direction has to be largest because you know that, I can't write it there, you know that 3 sigma is equal to 3 times square root, there's a 2 in there, isn't there? 2 dt. So they're all taken at the same time. And so the only way that this length can be longer in the longitudinal direction versus the transverse, since at the same time, is if this value is larger. And so it makes sense that the values that you get out of here are different, and they're related by the square root of the lengths, I suppose, right? So, yeah.
You said that our like transverse block or transverse dispersivity is like not representative because we assume that our velocity is small. Is that like a fair assumption to say that like our transverse dispersivity is the same as our V star, or is that not a fair assumption?
I'm not sure I said what you said I said.
Okay.
You said that the transverse dispersivity. So these are both the same granular material, and so if we're looking at this expression to look at the dominance of molecular diffusion over mechanical dispersion, you'd expect that both the ability to spread out laterally and longitudinally as it travels downrange is controlled by mechanical dispersion, not this. And so if you think that in traveling longitudinally, it's spreading because of this advective velocity completely overpowers this effect here, then if this coefficient is only a third of the magnitude of this, then you'd probably expect that it's really done by the mechanical dispersion of spreading in the aquifer rather than the fact that this magically becomes a larger number. These two numbers are very small, and they're the same, probably roughly the same. I guess you could argue they're slightly different, but they're perhaps orders of magnitude different from this, not just a factor of 2 or 3, right? So we said before, I have this, if you look at diffusion coefficients, molecular diffusion coefficients of contaminants in water, they're of the order of 10 to the minus 9 meters squared a second. And so these are in days for what we have, but I guess we could calculate what they are. Dispersivities are in meters squared per day. And so, and they're 0.019. So that equals 2 times 10 to the minus 2, so that's roughly 10 to the minus 2. How many seconds in a day?
86,400.
You're on it. 10 to the 5, right?
Yeah.
So this all of a sudden is divided by 10 to the 5. So 10 to the, no, it's not actually not far off. 2 orders of magnitude bigger. I didn't think it'd be anywhere near that close, but that's actually quite close. So, oh, I'm glad it's bigger. So this is bigger, right? Still, by 2 orders of magnitude. And so, yeah, so it's a function of that. So, very good. Where did you learn that?
My buddy had it said as his motivational quote on his home screen.
So when what temperature do Fahrenheit and centigrade scales cross?
Fair. I have no clue. 59.5.
Is that his license plate number?
No, is that it?
40, minus 40. Are both the same. Because my first job getting out of school was standing on an ice floe at minus 40 centigrade. Frozen river, not an ice floe. We'll talk about that later. So all right, so we can get them for that. So that's one way through a natural gradient tracer test. If you have one, or if you have a site where you could measure these things and you know something about the timing of stuff starting and having it evolve down gradient, you could perhaps estimate this behavior in situ. It turns out, and you can get good magnitudes for this, we'll come back to this a bit later. I guess this is just getting the value of alpha out of here. It turns out that if you look at taking a whole bunch of these, if you did this experiment at lots of different sites around the world, as someone did, Lynn Gelhar in this particular case, measuring for plumes of different sizes, the length of the plume is the scale, 10 meters long, 100 meters long, kilometer, 10 kilometers, and back calculating from what that plume looks like at its fringes ahead and behind it and in its width, I guess longitudinally in this particular case, and you plot what you calculate for this value of longitudinal dispersion. So remember, we have this term here is equal to alpha L velocity plus d star. We're going to assume that in our measurements this is 0. We're going to assume that we can know at this particular site what our advective dispersion is, our advective velocity is. And so if we know something about the shape of the plume, we can immediately calculate what this is. So if you do that at a bunch of places, you find something very strange. It's kind of a shotgun blast, but these are the results. They scale positively with the length of the plume. Bigger plume has larger dispersivity. If you draw a best fit line through them, you could imagine this best fit line might be the longitudinal dispersion is equal to the length scale, the size of our plume, divided by 10. 0.1 times x is this line here. It's on a log-log plot. That's the best fit curve perhaps, but you see that the envelope that includes all those points is pretty broad. It's a couple of orders of magnitude, at least one order of magnitude on either side. So this, if you're using this equation, you have to realize that it's kind of a shotgun blast that you're limiting to a line. And so why would this be that this is the case? Well, this is coming back to our idea that you don't use a fist-sized core to measure dispersion in the laboratory because it doesn't really sample all the heterogeneity in the system. And so the idea of this is that if you do an experiment at 1 meter, then it sees the fractures that are at that scale that can make the plume spread out at that scale. If you're doing it at a kilometer scale, then it sees a fault which might be able to take the stuff from where you're standing to 10 kilometers in the distance and therefore give the dispersion that relates to that. So the basic idea is that as you have a larger plume, it samples a bigger and bigger volume of your aquifer, and the chance of you finding a big, fast, high velocity conduit in that part of the aquifer increases, and therefore the dispersion goes up. And so if you want to have a value of alpha L, this isn't such a terrible one to use. And if you want to have a value for alpha T, then a value of alpha L over 3, which is kind of what we found out from the Borden site, isn't a bad number to use either, given that you don't have any other information. And yeah, and that's it. And that's kind of said here. But I think the main idea is that lab tests don't work very well for dispersion, but they do work for molecular diffusion. And so if you're designing a nuclear waste disposal site to get rid of low-level nuclear waste, and you're using clay, the surrounding clays as the barrier for stuff escaping, then measuring the dispersion in a clay sample in the lab is good. If you want to measure dispersivity in a granular or a sandy material or a silty material like at Borden, it's not very good. And the reason is because, one, it doesn't sample things very well. It doesn't sample the heterogeneity, which is important as you get to being at field scale. And so if you're designing at field scale, you'd want to do a test at field scale that samples that. And I guess the other damning factor is that if you do experiments that are not at the in situ velocity. They're not natural gradient experiments, but they are forced gradient experiments. Then, depending on the geometry of your test, you might get artificial dispersion in them. And also because you're forcing the fluid to flow at higher velocities than you expect, you're introducing probably more dispersion into it than is accommodated in this simple term here. It should accommodate it, right? If you're doing it at a forced gradient, you measure the dispersion, it should account for the higher velocities you're using, but in actuality, it doesn't. And so it turns out to be not very good for that. And so once we take that into mind, maybe we always use this idea here. And if we have that information here, then we can go back all the way here and to do our forward analysis to see exactly what our plume would look like in situ and what our breakthrough curves would look like, and when we can use these simplified ideas and when we can't. And so we're actually quite far along in our system. So we know that it may break through earlier because of dispersion. So we've solved this one question about when do we use this breakthrough curve. I guess we didn't address so much the value of whether the concentration when it arrives is still the inlet concentration or whether it drops. We know that if it's in you can imagine if it's in a one-dimensional problem, because it's so constrained, probably when it arrives downstream, it's pretty much the same. If we have a system which is either 2D or 3D, then what we can get is spreading both longitudinally, but more importantly now laterally. And so if it spreads laterally, so the volume that's included around the front is getting larger and larger, then we might expect that the concentration goes down. And we know indeed that's the case when we look at the case of a spiked upstream amount, just like Borden. We didn't look at the concentrations, but the concentrations as we went downstream in Borden must have been progressively smaller and smaller. We didn't use that information in any way. And so we know that as a function of spreading, we might expect concentrations to change. And so maybe we'll look at that. It turns out that also there's another reason why the concentration might change, and that is because the stuff it flows through might suck the contaminant out of the water and plaster it onto the static grains. And that doesn't work very well for the quartz, but if there's organic carbon in the system, it's just like putting stuff through your Brita filter. It'll move it, and if it's moved out of the water, then by definition, the concentration has to drop, because we're measuring the concentration in the water, typically. And so the next thing we'll talk about is attenuation and retardation. So attenuation means that it drops the concentration because it takes it out of the water and sorbs it onto the organic carbon. And retardation means that because it's doing that, it's taking the front and making it appear to go less quickly because it's taking mass out of it. And so not only will the front be canted over at the time of arrival, as we had here, not only will the front be canted over, but it might also be delayed in time and arrive later because it's no longer moving at this rate here, but it's being delayed in its arrival because the stuff in here is being sorbed, taken out of the water and attached to the static organic carbon. And since it's concentrations that we measure in the water, not in the solid, then it's depleting this area here. So advection and retardation. The end. Any questions? You've been very attentive.